Welcome back to the third lecture, or third video in this series, where we're trying to build up our Fourier knowledge. So this might get a little repetitive, but it's not so bad. If you recall, in the last two videos, we've been developing these building blocks. We've got one example building block, or basis function, called p of t, which has a value of 1 between the times of 0 and ts seconds. And when we're using this basis function and scaling it to approximate any general x of t function with x hat of t, which, as said, is the infinite sum of scaled basis functions. In this case, the basis functions are time-shifted p of t's. So let's summarize all this in the context of approximating periodic x of t functions. So first we talked about representing a function as a sum of scaled basis functions. We just went through that. Then we talked about minimizing the integrated squared error to determine those scaling coefficients, the c sub k values. We then presented the orthogonality principle and talked about how that can be used to minimize the integrated squared error. Then we talked about if the basis functions themselves happen to be orthogonal, then it makes solving the orthogonality principle equations easy. It still begs the question which orthogonal basis functions to be used. So for these periodic functions, we propose to use sinusoidal basis functions. And we're going to use the exponential representation of these sinusoids. In this case, we have an exponent to the jk omega naught t. So let's look at each one of these quickly. J, this is our unit imaginary number, which is equal to the square root of -1. K is an index corresponding to the index of the basis function. So for the kth basis function, we're going to have a k here. And that actually is going to be multiplied by our fundamental frequency, omega naught, then times time. So we've got our unitary imaginary number. We've got a frequency, which is an integer number of our fundamental frequency times time. So what you'll get is for each basis function, you're going to get a different frequency associated with it. Now, the fundamental frequency, note, is defined as 2 pi over t naught, where t naught is our fundamental period. We can write this out with our cos and sines as cos of k omega naught t and j sine of k omega naught t, which you should be familiar with. But let's get a bit more familiar with this in the third activity. And the first thing we're going to do is show that such a basis function, using this complex exponential sinusoid, is actually orthogonal. So I want you to pause and think about this. How would you show that? I'll give you a hint. Go back to the original definition we gave you of orthogonal basis functions. Well, here it is, in case you forgot. Basis functions m and k are orthogonal if the integral over time of their product of one with the other's complex conjugate is equal to some constant if it's the same basis function, small k equals small m, and it equals 0 if they are actually different basis functions. So using this definition, we can pretty easily plug in our exponential basis functions, or our exponential sinusoids from the previous slide, to determine if they're orthogonal. I'll let you get a pen and paper and try to work this out. Pause the video until you're done. Have you finished? All right, let's move on. So to start, we're going to substitute e to the jm omega naught t and the other basis function e to the jk omega naught t. Notice I put a negative sign to indicate the complex conjugate. When I multiply them together, we can get a single exponential times j. Again, remember, this j is not an index. This is the square root of -1, the unit imaginary number. But these are two index, or these are two integer values, m and k, all times the fundamental frequency times time. What we're going to do on the next slide is look at when m equals k and when m does not equals k, and see what happens to this equation. I just rewrote that same equation from the last slide. And like I said, let's look for the case where m equals k. If you recall, when m equals k, we should get a resulting constant value for this equation. Substituting in m equals k, you're going to get a 0, and an exponential to a 0 is 1. Integrating over the fundamental period from 0 to t naught, will give you a value of t naught, which is a constant. Great. So far so good in checking that these basis functions are orthogonal. We'll start just like we did on the last slide, only we'll look at the case when m does not equal k. So if m and k are integers, then m minus k must also be an integer, which in this case we're going to call n. So n is equal to m minus k. Integrating this over some fundamental period, 0 to t0. So when taking the integral of an exponential, you get 1 over the term in that exponential. Again, this is integrating with respect to time, so that t should disappear down here. And you're integrating it from the time bounds of 0 to t naught. Plugging those two in, 0 and t naught, you'll get e to the j n omega naught t naught minus e to the something times 0, which will become a 1. Now, something to note is omega naught and t naught are related. If you recall, omega naught is actually 2 pi over t naught. Now, those two t naughts will cancel, and you've got an e to the j n, which is an integer, times 2 pi. Well, that's going to just give you a value of 1. So we have 1 minus 1, which gives you 0. So for the case where m does not equal k, that is two different basis functions, you're going to get a 0 for this equation, which tells you that these exponential sinusoids are in fact orthogonal. Great! Let's use them within our original function, which is the sum of infinite scaled basis functions. And by the orthogonality principle, we showed that we can calculate the scaled coefficients associated with each basis function as such. But for our particular case, when the basis functions are these sinusoidal exponentials, we can substitute those in for the basis functions, as well as for how we calculate the coefficients. In this case, you can see that the complex conjugate of the basis function just produces a negative sign on the exponential. And we can also see that the denominator term here, we calculated on the previous slide, to be t naught. To summarize, any periodic signal can be represented as an infinite sum of complex exponentials, as such, where the scale coefficients can be written this way. Just to remind everyone, k varies from negative infinity to infinity. That is, we have, in this particular case, an infinite number of basis functions for an infinite number of scaled frequencies. Let's do one last activity within this video. In this case, I'm giving a continuous valued signal, x of t, which is a sum of two scaled cosine signals, each with a notably different frequency. I'm giving you a fundamental frequency of 2 pi radians per second, and I'm asking you to calculate the coefficients that we would use to represent this signal with a Fourier series. Now, in this particular problem, we're not going to use all the fancy integration that we used last time. We're just going to almost play a matching game. I want you to think about that for a minute. See if you can write out this x of t as a function of scaled exponential sinusoids. Have you done it? If you have, let's move on. If not, pause. All right, let's start with our original signal. And I'm just going to write out the two different frequencies in terms of an integer value times the fundamental frequency, where the fundamental frequency was 2 pi radians per second. This might give you a hint. You might want to pause and do the rest on your own. Or let's just keep going. We're going to substitute in, for the two cosine functions, what we know to be true for our exponentials. That is, cos of 5 omega naught t is e to the j 5 omega naught t plus e to the negative j 5 omega naught t, all divided by 2. Similarly, for the next cosine function. Let's split those up. Now, this should start to look like a sum of scaled complex exponentials. See where this is going? It looks like our typical Fourier series representation. And in this particular case, we know that 1 is going to be C5, 1 is going to be C to the negative, or C underscore negative 5, 5 is going to be our C1 value, and 5 is going to be our C underscore negative 1 value, just by playing a matching game. So for our original signal, we have these coefficients. Note that there is no C0 or constant term here. Hope this makes sense. Let's summarize all this. Any periodic signal can be represented as an infinite sum of complex exponentials, where the complex exponentials are sinusoids, and they are also orthogonal, as you just proved.